Okay, yeah. So the topic for today is DP optimizations. This is the second lecture. This is just a typo. It's actually divide and conquer plus 1D plus Knuth. Maybe you guys haven't heard of the 1D optimization. It's relatively, I would say, slight like people know less about it, but it's quite applicable. I would say 1D is a better optimization or more relevant for competitive programming than Knuth. Divide and conquer is definitely probably rank one amongst all these three. So that's that. Our agenda for today will be broadly discussing the quadrangle inequality, followed by divide and conquer, then 1D. I'll briefly go over Knuth. I have just one example for Knuth and also like not fully fledged. Majority of the sources that I've accumulated are from Arjun Arul's lecture that's there on YouTube for free. You guys can watch that also if you want. It's slightly disorganized, but Arjun's way of explaining things is very good. It's this lecture. So yeah, cool. So we first go over quadrangle inequality. What is quadrangle inequality? Quadrangle inequality is an inequality on the cost function of a DP. And if you get this inequality for a given, like you encounter a DP question and you observe that the quadrangle inequality is satisfied by the cost function of that DP problem, then you're pretty much good to go with one of these optimizations. You could be probably be applying divide and conquer or 1D or not. Note that, so the way I would phrase it is this way. Quadrangle inequality is sufficient to do a DP optimization, but it is not necessary. That is, if you get quadrangle in the cost function, you'll get some more additional properties, which we'll discuss later, because of which you'll be able to apply the optimization. But if you don't get quadrangle, you still may be able to apply the optimization. It's just that it might be non-trivial to prove that can you apply the optimization or not. In all these optimizations, I would say the theoretical or the tricky part is that a lot of times you are unable to prove that the optimization will give you a correct answer here or not. Is that optimization even valid for this question or not? The implementation part for these optimizations in general is easy. It's not like segmentary or anything of that sort. It's like the implementation ideas used in these optimizations are straightforward. I would say the more convoluted part is, can we apply them or not in a given question? Okay, so let's go over quadrangle inequality. What is quadrangle inequality? Quadrangle, so this is the simplified version of quadrangle inequality, which even Arjun uses in his lecture. And I like this one much more than the generic one that you'll find on the internet. It is the same as the popular, like if you search on code courses, you'll find like some other inequality, but it's the same one, just rephrased. Here, C is our cost function. And what we are trying to say is that the cost function, okay, so let's take an example first and then go through quadrangle inequality with that example in mind. That way it will be much more intuitive. So I'll take the example for the first optimization, which is divide and conquer. The problem we are discussing is seal and gondolas. It's a problem E on CF. I have the link on the side. You guys can open the CF link as well if you want. What's the problem? The problem is that there are n people and you want to group them into k gondolas. They come in a specific order. All those n people have come in a specific order from 1 to n. You'll put some q1 people in the first gondola. Gondola is just a vehicle. So you'll group the first q1 people, then group the next q2 people, and then eventually group the k people, last k people. So you're basically dividing an array or like a bunch of people, n people, into k segments, subsegments, right? And note that sum of all your QIs should be equal to n. That is, you're basically just grouping all of them. What's the cost of the grouping? So you want to minimize the cost of the grouping. And the cost is that within a given group, the sum of all the UIJs is the cost, the unfamiliarity of people with one another. So take an example. And so that's the cost, and you want to minimize the sum of the costs. This is all the things are written here. People don't want to stay with strangers in the gondola, so your task is to find an optimal allocation to make people happy. For every pair of people, I and j, there exists a value uij that denotes their level of unfamiliarity. You can assume symmetry on this matrix and that a person is not unfamiliar with themselves, which is intuitive. Unfamiliar value of a gondola is the sum of all the unfamiliarities between every pair of person in that gondola. Make sense? Total unfamiliarity is the sum of all unfamiliarity over all the gondolas. You want to minimize this. N is 4,000. K is 800. The number of people in the queue, blah, 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 blah. Okay. Now let's see an example. This is an example. N is 3, K is 2. And this is your matrix, cost matrix. So you have 3 people, you want to group them into 2 groups. So you have the person 1, person 2, person 3, right? Person 1, if he wants to be grouped with person 2, his cost is 2 units. Person 2, if he wants to be grouped with third person, his cost is 3 units. What will you do? One way you could do is you could just group all of them in one box, but that will give you a cost of 5. And also you actually have the ability to make 2 different groups. So why would you ever group them in one group, right? So that's unintuitive. What's the other alternate? Maybe one alternate is that you group 1 and 2 in one group and 3 alone. In that case, the cost of this is 2 and the cost of this is 0. The reason the cost of this is 2 is because 1 with itself has unfamiliarity 0 and 2 with itself has unfamiliarity 0. So you'll just sum up this matrix on the upper side, and similarly 3, 0. So 2 plus 0 is 2. The third alternate option that you have here is which is strictly verse 1, 2, 3, and you group 2 and 3 together and 1 is alone. In this case, your cost of 2 and 3 grouping is 3, and for 1 it's 0. So the sum is 3. So what's the best one? To group 1 and 2 together and 3 alone. So do you guys understand the question in the first place? It's basically, I can add a page here and just give some more color to it. It's basically, you have this cost matrix, right? What you'll be doing eventually is like, say you decide that the first 5 people will be grouped together. So you'll be summing up the first 5 elements of like a 5 by 5 grid of that matrix, all these costs of that matrix. Then maybe the next 3 people group together. So you'll be summing up the 3 by 3 grids, the things that I'm highlighting in yellow. You'll be kind of summing up these portions, right? And maybe the last group is of 2 people. So you'll be summing up the group of size 2 here. I'm only summing up the upper right triangle just because of symmetry. You don't want to count the same pair of people twice. And you want to kind of divide them into like K groups such that your total cost is minimized. Right. In this example, I'm saying that there are total 10 people, and maybe one way to divide them is 5, 3, 2. The first gondola takes the first 5 people, the next gondola takes the next 3 people, and the last gondola takes the last 2 people. Maybe there is a better allocation, but like that's the general idea of what you want to do with this question. So what's the cost function in this question? Cij intuitively denotes the unfamiliarity in the group from I to j. So if all these are your people, then when all the people from I to j are in the same group, what's the total unfamiliarity? Which is I goes, let me use a different variable. A goes from I to j, B goes from A plus 1 to j, and you're summing U, A, B. Yeah, let me just share my screen again. I lost it. Yep. So that's the cost function, right? So the cost function is basically like, if this is your I point and this is your j point, the yellow region is your cost function. So notice in this case, can you argue that the quadrangle inequality is satisfied or not? So what is the quadrangle inequality? The inequality says that the incremental difference in the cost function. So your cost function, think about it this way. There is this index I, there is an index I plus 1, there is an index j, and there is index j plus 1. What the inequality's left-hand side is saying is the incremental cost to expand your window from ij plus 1, sorry, from ij to ij plus 1. That is, originally maybe your window was of size ij, but you expanded it to ij plus 1. And that incremental difference that you get, that is your left-hand side. So the like intuitive, like, yeah, the subtraction of the two. This must be greater equal the incremental difference that you get had you not started from I, but had you started from I plus 1. That is from I plus 1 to j plus 1 minus from I plus 1 to j. That's the right hand side. So what you're saying is that the incremental difference of a larger chunk being increased by 1 unit is larger than the incremental difference for a smaller chunk being incremented by 1 unit. And do note that when we are referring to the cost function like this and saying that the incremental difference should be larger, we are talking about min dps. That is, in this dp, our objective is to minimize the entire dp. That's the general assumption that quadrangle works under. If you have a dp that's a max dp, that you have to take max over a lot of things or something of that sort, like you're trying to maximize your objective function, in that case, just treat this quadrangle inequality as reversed and try to prove it the reversed way, and it works. But like, for generally, like at least in this lecture, we'll be mostly covering it on the min side. So that's when you say that the incremental cost increases. Now, you don't get this for free in a lot of questions. For example, there is this classic question called matrix chain multiplication. You can Google it if you want. Chain multiplication. Or maybe you can think of other examples like, I don't know, longest increasing subsequence. Probably not, but like you can construct examples of DP questions where this inequality is not satisfied. And whenever this inequality is not satisfied, more or less, you probably won't be able to apply one of these optimizations. I'm still saying it's a sufficient condition, not a necessary condition. So you might still be able to apply it. Okay, but in this question, let's see, seal and gondolas, do we get this for free? Do we get the quadrangle inequality? You'll notice that we get this, reason being our Cij is this much, right? So it's a, intuitively, Cij is basically a submatrix sum halved because you're taking only the upper triangle, right? And if you expand from ij to ij plus 1, you're basically increasing the rectangle's amount by this much, right? And if you started from I plus 1, then you would have this rectangle minus this rectangle. Notice in the, sorry, my bad. I think, yeah, the way to explain it would be this. Say this is I, this is I plus 1. So this is I. So if you go from ij to ij plus 1, you are adding this portion, right? And this is also actually I, but this is I plus 1. But if you go from I plus 1, you'll actually be adding somewhere like here, you'll be adding this portion. So you'll notice that the inequality comes from the fact that this difference is actually additional on the left-hand side. I mean, you can work out the math if you want, but I just wanted to show you pictorially what it looks like. If you work out the math, you'll find that the value of uij plus 1 will have been only added in the left-hand side, but not in the right-hand side, because the right-hand side only starts from I plus 1. So you'll never get values that have I in them. So uij plus 1, this particular entry, you won't get on the right-hand side, but all the other entries, you'll get them both on the left-hand side as well as on the right-hand side. So that's why the left-hand side has to be greater equal, depending on whether uij plus 1 is 0 or non-zero, whatever. So you see that quadrangle inequality is satisfied. So what's the general idea of divide and conquer solution, you get the quadrangle inequality. It gives you something for free, which is basically the magic step. We won't prove this, but it's like a well-known thing that quadrangle gives you some things for free. And once it gives you some things for free, then you can apply the divide and conquer technique actually. Just as a poll question, what will be the slow recurrence for this question? Your constraints were n and k. We'll first go over the slow solution, which is order n square k. Once we have the slow solution, I'll define the opt function, which is a very common function that we define in DP optimization of this sort. And we have already proven that the quadrangle is satisfied for this question. And then we'll go on the DMC trick. So I know we only have a couple of people on this class, maybe actually just one. Sorry, do you have any inputs on what the DP recurrence will be for this question, the slow recurrence? Sort of to me, direct message, DPIJ being, let's see. So you're saying DPIJ cost if I to j people are in one gondola. That is the cost function, which is fine. Like what you are defining as DPIJ is more like the cost function. Okay, let me first define what DPIJ will be, then maybe you can come up with a recurrence. Let's say in our definition of DPIJ will stand for the first I people. We have divided them into j gondolas. Into j gondolas, whatever gondolas. And what is the minimum cost of that? That is what DPIJ is trying to define. If that is the definition of DPIJ, that for the first I people, so let's say these are all my people, then for the first I people, I may have one group here, one group here, one group here, and these are like three groups in this example that I'm pictorially drawing, but maybe there are more. What's the minimum cost to build up this? In this case, if you could construct DPIJ, then you can see that our answer will be stored in DPNK. That for the first n people, that is all the people, what is the cheapest way to divide them into gondolas? Right. So given this definition of DPIJ, can you come up with the recurrence? Okay, so we have a couple of more people joining. Maybe I'll probably have to rewind this a bit. Yep. So yep, that's probably correct. Not the max function, but like the cost function, the CUAB, whatever that. Because we are summing over all the submatrices, the entire submatrix. Okay, so for all the people who joined just now, I'll briefly go through the notes again. So this lecture is on divide and conquer plus 1D plus Knuth, and we'll be going through quadrangle inequality and then divide and conquer, then 1D, then Knuth. Knuth is probably the least useful out of all these optimizations. Quadrangle inequality is basically an inequality on the cost function of DPs. And if you get this inequality in a DP question, you're pretty much guaranteed that you can apply one of these optimizations. It's a sufficient condition. It's not a necessary condition, the quadrangle inequality. Meaning that if you get quadrangle inequality, you can definitely apply one of these optimizations. If you don't get quadrangle inequality, you could still be able to apply one of these optimizations. But it's one of the core principles of all these optimizations that quadrangle has to be satisfied in most of the cases. I mean, as I said, it's a sufficient thing. It's not a necessary thing. So there might be cases where even without quadrangle, you can still apply these optimizations. Another thing to note is that the implementation part for any of these optimizations is the easy part. The proving part of whether this optimization will work for that particular DP question that you're encountering, like whether it will work or not, that's the hard part. That's the general idea of DP optimizations. The implementations are generally easy. Unlike CHT, convex hull trick, where the implementation itself is quite tedious a lot of times, the implementation for all these three is relatively straightforward. I would say 1D, 1D is slightly tricky, but like Knuth and Divide and Conquer are pretty simple to implement. So the question that we're doing we'll first cover Divide and Conquer. I'll first go through the question that we're doing. And once you understand the question, I can explain the cost function and just justify why the quadrangle works for this particular question. So the question is as follows. It's a code forces question. And the question is that there are n people. You guys can open the link of this question on the Discord channel of classes. I have shared the slides link, so you can just open the link from there if you want. And this lecture is being recorded if anyone wanted to ask that. So yeah, so the question is as follows. You have n people and you have to divide them into k gondolas. Gondola is type of grouping, like a vehicle in this particular question. And the first Q1 people will go into one gondola, the next Q2 people will go into the second gondola, and so on. The last QK people will go into the kth gondola. And you basically, all the people have to go on one gondola or the other, and they're going in continuous segments, right? What is the cost of allocating people in some way or like splitting people in a specific way? It is this particular line. So people don't want to stay with strangers in the gondola, so your task is to find an optimal allocation way. That is, find an optimal sequence Q to make people happy. For every pair of people I and J, there exists a value Uij to denote their level of unfamiliarity. You can assume symmetry, and you can assume reflexive, that Uii is 0. Then for a given gondola, the cost is the sum of all the unfamiliarity between every pair. Total unfamiliarity is the sum of all the unfamiliarity over all the gondolas. So if you take an example like this, where you have like 10 people and you have your cost matrix, your U matrix given like this, then you might have one allocation which says the first 5 people will be one group, the next 3 people will be another group, the next 2 people will be another group. That is, you in total have 3 gondolas because you're making 3 groups. In this case, your costs will be for the first 5 people, your cost will be this portion of the matrix, the portion shaded in yellow. And for the 3 people, it will be something like this. And for the 2 people, it will be something like this. It's basically like sum of submatrices of the U big matrix. I'm not summing the entire submatrix. I'm only summing the top right portion just because of symmetry, because I don't want to sum U12 as well as U21. A single pair has to be only counted once in the cost function. So this is a example for this particular question. You have 3 people and you have 2 gondolas, and this is your matrix. So you have 1, 2, and 3. You could group them as 1 and 2 in one group and 3 in the other group, or you can group them as 1 in one group and 2 and 3 in the other group. You'll find that the first option is better because in this portion versus this portion, your sum is only 2. Whereas if you go the other route, that is this portion and this portion, then your sum is 3. And you want to get the cheaper one. So you'll group 1 and 2 together, and the third one will be alone. Any doubts understanding this question? Because like for the next 15 minutes, we'll be just discussing this question, divide and conquer optimization or whatever. So it's imperative that you guys understand the question in itself. Okay. So now we'll go through what's the quadrangle inequality. So for a given DP question, let's see, we define the cost function of that DP question. then quadrangle inequality basically states, in this case, in this particular question, your cost function is defined as this Cij. I've written it somewhere here. Yep, it's this thing. I'll just shade it in yellow. So Cij is the sum of the entire submatrix from I to J, and you're just adding each element once, not the mirror image, so the yellow region. Because if all the people from I to J are in one group, then Cij defines the cost of that group. That's what Cij is trying to say, right? So that's the cost function in this case. And what quadrangle inequality in general says, it's not particular to this question. It's a very generic inequality that DP questions try to we'll try to exploit in these optimizations, is that if the incremental difference, okay, so 4 indices are important here: I plus 1, j plus 1. This is the thing, right? So 4 indices are important. And what the quadrangle, okay, first off, there are like two variants of quadrangle inequality. The one that I'm mentioning here is the easier variant, and like easier to understand, easier to digest. I copied off this variant from Arjun Arul's lecture on Unacademy. It's a pretty good lecture if anyone wants to watch for DP optimizations. His way of explaining these things is pretty good. And I've also shared the link here. It's a free lecture on YouTube. I've copied out a lot of ideas from that one. So the inequality that quadrangle uses is this: if the incremental difference of the cost function from I to j plus 1 minus I to j, what does that mean? That if your cost function is already from I to j and you're expanding it by one position, that is going from I to j, instead of I to j, going from I to j plus 1, that is adding this green portion intuitively, this incremental cost is greater than the incremental cost had you started from I plus 1 instead. Instead of starting from I, you would have moved to I plus 1 and tried the same thing. That is from I plus 1 to j plus 1 minus I plus 1 to j. Then that incremental cost is smaller than the incremental cost had you started from I. So intuitively, if the cost function says the incremental difference is larger for a larger chunk, then the quadrangle is satisfied. And this has to hold for all ij, like I less than equal j. Also, another thing to note here is that this quadrangle is only for min DPs. When I say min DPs, I mean DPs where you are trying to minimize the objective function. If in this question, we are trying to minimize the total cost in the Gondola question. If you have a question where you're actually trying to maximize something, then you'll just treat this inequality in reverse and try to prove the reverse thing. So is the quadrangle inequality, like, does everyone understand what the inequality is stating? I get the point that you might not think that why is it useful to get this inequality? That's another thing. But like what the inequality in itself states, that this difference that you get on the left-hand side should be greater equal the difference on the right-hand side. That's all what we're trying to say. Okay. So in this particular question, you can prove that the cost function that we had, which was this thing, actually satisfies the quadrangle inequality. An intuitive way to think about it, like, or visualize it, is your cost function is the submatrix from I to j, right? So on your x-axis, you have I, j plus 1, j, I plus 1. On your y-axis also, you have I plus 1, j plus 1, j. Right? And this is with respect to a bigger matrix, this U matrix that you have, right? And these are the 4 indices that you care about. Notice what's your cost from I to j plus 1 minus cost of I to j. Cost of I to j plus 1 is this entire submatrix, and cost of I to j is this thing. So the additional portion is kind of like this. I'm excluding everything below this because we don't count this portion. We are only caring about the upper right side. And what is your cost from I plus 1 to j plus 1 minus I plus 1 to j? Again, it's almost like instead of starting from ith position, you're starting from I plus 1th position. So from here to this triangle minus this triangle, if you look carefully. So it's basically, let me shade this in orange. It's basically this difference, right? So notice that this particular position, which is uij plus 1, this particular position only got added on the left hand side of the inequality. On the left hand side of the inequality, but not on the right hand side. And everything else, all the other terms that you will see here, have been added on both the left hand side and the right hand side. So that's why the left hand side has to be greater equal, because this particular value is greater equal 0. The uij plus 1. There are no negative values in this matrix. That's a constraint given in the question. You are given that all the values are positive or like non-negative, basically. So it can be 0, but like you only want greater equal. You don't want a strictness. So we can see that the quadrangle is satisfied. You can even work out the algebra if you were not convinced by the pictorial representation. Okay, so we have the quadrangle inequality satisfied. Now we'll discuss what's the slow solution for this GP. So in all these GP optimizations, obviously the first step is just to come up with the slow solution. And the following step is maybe try to prove the quadrangle inequality or something. So I'll define this opt function also following this, and then we'll see how the magic of divide and conquer works. But first we have this poll question, that what is the slow solution for this GP, which is n square k. Note in this question, n square k doesn't work. You probably want something like nk log n, like just as a runtime thing, because like n and k are large enough that n square k will not work. So if you guys have any ideas, I think Saurabh had cracked it more or less on like how the n square k thing will look. But I'll just explain here what's n square k. If any of you also have input on the n square k, just comment on the chat or something. It's basically dpij equals. So what we'll try to denote by dpij will be the first I people have been split into j gondolas. What is the cheapest way to have done that? And that would be something like dp alpha j minus 1 plus c alpha plus 1 to I. And we'll take the minimum over all alphas less than I. What I'm trying to say here is, so that's the way how I write alpha. Maybe you guys write alpha in a different way. I just did not want to use the variable k. So that's why I came up with the Greek word. What we're trying to say is, let's say these are the first I people. So if the ith person belongs to the jth gondola, maybe that gondola is of size this much, then the last person that was not on the jth gondola, let that guy be alpha. So the first alpha people were split into j minus 1 gondolas in whatever way, which was dp alpha j minus 1, the cheapest way, plus the cost of splitting, sorry, not the cost of splitting, but the cost of putting everyone together from alpha plus 1 to I in the same gondola, which is basically the sum of that submatrix from alpha plus 1 to ith index. This entire thing gives you one possibility of splitting at the position alpha. And you could have changed alpha to some other place and like tried all different possible alphas, basically the last splitting point of your chunk, right? And whichever is the cheapest, you just go for it. So in this case, if this is the recurrence, is it clear to everyone that our answer will be just dpnk? That is, what is the cheapest way to split the first n people, that is all the people, into k gondolas? So again, I have a question here, like, is this part clear to everyone, the slow dp itself? Because if the slow dp is not clear, it probably will just be convoluted to go for the faster thing. Okay. So if this is clear, let me add a page here. Yeah. So we'll now define opt_ij function, which is a pretty useful, it's a very generic trick that like, or a very generic concept. You probably have thought of this concept even before. What opt_ij is trying to, okay, one more thing. Let's just swap our dimensions. This is for the ease of explaining divide and conquer, nothing else. So I'll actually write the recurrence as this dpkn. That is k gondolas to do first n people. So dpkn is minimum of alpha less than n, dpk minus 1 alpha plus c alpha plus 1 n. I'm just swapping the two dimensions. It doesn't really matter in this particular question. I'm just doing it because the optimization actually happens on the second dimension. So it becomes much more intuitive when I argue about things. And yeah, so okay. So the thing I wanted to discuss here was what is opt_ij. In this question, opt_ij is basically, so notice in this DP recurrence, right? You have a minimum over a couple of things. And this minimum wins at some place. Maybe alpha equal 5 give you the winner. Maybe alpha equal 7 gives you the winner. Winner meaning the minimum most value. So whatever that argument is of alpha at that place, that is what opt_kn is trying to denote. So opt_kn is basically the best splitting point. That is alpha in best splitting point for dpkn. So is this part clear? That when you're calculating dpkn, whichever alpha gives you the smallest value of this dpkn, that particular alpha is actually your opt_kn, basic, like trying to denote that where was that splitting point. And like you guys would have seen this kind of idea also in questions of DP where you're trying to reconstruct the solution. That the question not only asks you to give the cheapest cost, but also asks you to recover how the cheapest cost of that DP question is made. That how is the grouping done actually? In those kind of scenarios, also a lot of times you'll store this opt array or like name it something else, but like conceptually store this opt array that where all did I do my splits for to get the best TP. And then you'll recover your like backtrace your answer from that. It's a common enough technique, I think. So is the opt function's definition clear? It's basically the, if you want to think about it more mathematically, it's the argmin for this recurrence. That is, where did this argument hit the minimum value? Any doubts here, or is it clear? Because like again, this like understanding these basic fundamentals is very useful or relevant to actually be able to apply the divide and conquer technique. Okay, so if there are no questions, I'm assuming that this is clear what the opt function is trying to represent. Otherwise, if there are questions, just ping them on the chat. So you got quadrangle inequality. What that gives you for free, now the magic part of this thing, is as follows. Quadrangle being satisfied, which we showed above by this argument that uij plus 1 is the spare part in this inequality. Quadrangle being satisfied gives you this for free, which is, it gives you that the opt function, not the dp function, okay, maybe the dp function also, but the opt function is monotonic. That is, it's always increasing. That is, opt_ij is less than equal opt_ij plus 1. Notice it's only talking about the second dimension and not the first dimension. That is the j and j plus 1, not the first dimension. In this question, the second dimension is of the nth thing. So it gives you this monotonicity. And this monotonicity is super useful. Okay, I think this is probably wrong. It's for all I comma j. It's not for less than equal. The reason this happens, I don't have the proof offhand, but it can be proven. It's just a bunch of algebra. I can probably share some slides with you. But it's not that trivial to prove. I mean, you guys can try it out, but I won't recommend, like, I won't expect that you'll get the proof in like say 20 minutes or something. It is relatively complicated. I've gone through it once. That how does quadrangle provide us enough support to prove this? But it does hold true. Irrespective of the question, if your cost function of that question satisfies quadrangle, you get this for free. That opt ij is monotonic. And that's the only thing that's required to apply divide and conquer technique, that your opt ij function has to be monotonic. Now, maybe quadrangle for a given question is not satisfied, but still somehow you can prove, or somehow you know intuitively, that your opt ij function is monotonic. Even in those cases, you can apply divide and conquer. That's why I'm saying that quadrangle is sufficient, but not necessary. Okay. So now just assume for now, we won't go through the proof itself, that opt ij is monotonic, that is, this holds. In that case, how can we leverage this to actually apply the divide and conquer technique? Now that's the question, right? So notice how your DP table will look like. Your DP table will look something along these lines. Your K will go from 1 to capital K, and your N will go from 1 to capital N, and you'll be filling out values. And the last value is the value that you're interested in. That's what your final answer is. And also notice, based off your recurrence, that dpkn is dependent on the previous row, that is k minus 1, alpha, and the cost function. So each element here can be calculated if we know the entire previous row. Is that correct? That a given cell can be calculated if we know the entire previous row. The slow way to do this is that you loop over the entire range of alpha, right? This alpha goes from like everything. That's the slow way to do this. So if you're trying to calculate, say, this particular value, then you're like, for this specific k and for this specific n, I have to split at some point before this n. So my alpha can be in this range. Maybe this guy, so on. And the remaining cost function I'll add here. And I'll try all these values, which is the slow part, right? Now, how do you optimize on this? You know that your opt function is monotonic. So what you're getting for free is kind of this. In this particular matrix, if you're looking at a given row, let's think of this now as opt matrix. K goes from 1 to capital K and N goes from 1 to capital N. Then your opt function is increasing like this, right? This is the value of a given opt K of N, some small k, small n. If you know the value of opt K of N somehow, because you did the slow calculation for this particular K N pair, then when you're doing the calculation for this guy, can you exploit the fact that you already know this value? Say this value is, I don't know, 12. How can you exploit knowing this value when you're calculating the opt kn for this guy? Or when you're calculating the dp for this guy, the one guy that is to the right of him. Notice that he has to be larger because the monotonicity holds. So you know for a fact that this guy has to be bigger than 12 or whatever that opt kn was. So you don't have to try all the alphas. That's the idea. You only have to try the alphas that are possible because of the opt condition. So the way it works is, so just remember that row wise, the opt function is monotonic. So for a given cell, what you'll do is you'll calculate the mid value, that is k comma n by 2. You'll first calculate this dp and opt, both of them, because when you're calculating the dp, you'll get the opt for free. And this will take you slow, like this will take you order n time. Now, once this is calculated, you'll say, I want to calculate n by 4th position and 3n by 4th position. So k comma n by 4 and k comma 3n by 4. Notice when you're calculating n by 4, you won't actually loop all alphas. You'll only loop alphas from 1 to opt k n by 2. Because you know that opt of k n by 4 has to be smaller than opt of k n by 2. So you won't find a better candidate beyond k n by 2, beyond the opt of k n by 2. The opt of k n by 2 is not required to be in the middle. It could be somewhere to the very left on the previous array. But you know that you only for k comma n by 4, you only have to loop from 1 to k n by 2. And similarly for 3n by 4, you only have to loop from opt k n by 2 to n. Again, because your opt for 3n by 4 cannot be smaller than opt of k n by 2. So you reduce the sample space that you're searching your alpha on. And notice the combined sample space of the search is total 1 to n. So these two sub-problems combined can be solved in order n. And you keep on recursing. That's the general idea. So k n by 8, 3n by 8. And here you get k, what will it be? 5n by 8 and k 7n by 8, I guess. Right? And each of them will be, so k n by 8 will be upper bounded by the opt of this guy. K 3n by 8 will be lower bounded by the opt of this guy, but upper bounded by the opt of this guy, 3n by 4, and so on. Okay, not 3n by 4, my bad. It will be upper bounded by the opt of 3n by 8 is somewhere here on the number line, right? Here. So it will be upper bounded by kn by 2. And again, this layer will also cost you order in total. I mean, that's the thing that I'm trying to reason here. And as you go down, you'll have at most log n such layers where calculating each layer will cost you order n. So total cost is n log n. And that's for a given k. That is for a given row. You did it in n log n. So total cost is k n log n. Which parts are not clear to everyone? I mean, it's not expected that like the time complexity part or the idea on how we are binary splitting, what all is unclear. I can just go through that again or explain it in better words. You can put it on the chat or you can just unmute yourself, whichever works. I don't expect this to be that easy to understand. And another thing I think you guys can take a look at is the CP algorithms website. That's also a useful resource. But yeah, go ahead in the chat if any of these portions is unclear. How to know which parts to search? Please repeat. Okay, fair. That's a good question. Maybe I'll draw this diagram again. Okay, so this was our DP, right? K going from 1 to capital K and going from 1 to capital N. And we were trying to do calculate a given row. Okay, first you understand the slow solution, right? That for a given K comma N, if you're trying to calculate it, you'll just run over all the alphas. That is for this, say this is, take this example. Let's say this is K comma 12 that we are trying to calculate. Then what you'll do is you'll do alpha equals 1 to 11. Let's just try that entire range and be done with it, right? Let's say you do that and you get the best alpha. Let's say the best alpha is at alpha equals 6. So best alpha for this guy is alpha equals 6, right? So in your opt array, you would have filled a 6 here. In your opt array, what does opt array denote? That what's the best alpha to fill this DP value? You got the DP value, you also got the opt value. You did it the slow way. You calculated the cell. Here, obviously, I'm assuming you're doing a bottom-up DP. So you have already calculated these entire rows above you. These are already calculated. That is being assumed. Your objective is to calculate this DP row in n log n somehow. Because if you can calculate each DP row in n log n, you're done. You can do the entire thing in kn log n. Now, for this thing, I wasted a lot of time because I searched for all alpha from 1 to 11, which is a lot of time because say my n is actually 20. So 1 to 11 is basically order n in some way, right? I'm just taking hard numbers here just to give you an example of what's happening. And say the best alpha I got was for alpha equals 6. Now, when I try to calculate this guy, which is say k comma 5, this guy was k comma 12. Now I'm trying to calculate k comma 5. When I'm trying to calculate the DP for k comma 5, my range, okay, not k comma 5 actually. Let's take some extreme example. Let's say this is actually k comma 9. It's somewhere to the right. So visually, this guy is like somewhere here. Right. So now you're trying to calculate k comma 9. Now you're in the slow solution. What was your alpha range? Your alpha would be from 1 to 8. That it can be split from anywhere from 1 to 8. But you know that opt k of 9 is less than equal opt k of 10, which is less than equal opt k of 11, and so on. Right? Basically, your opt function is monotonic. That is, it's increasing. Because you have this property, you know your opt k of 9 is at most 6, because opt k of 12 is already calculated here. So you know your opt k of 9 is at most 6, which gives you what? It tells you that your alpha for this particular guy, k comma 9, your best alpha can never be 7 or 8. Your best alpha. There is no point trying alpha equals 7 or alpha equal 8 because they won't be optimal because of the monotonic constraint on the opt array. So you can reduce your search space of alpha from 1 to 8 to 1 to 6. This is the crux of the optimization. That instead of searching the entire alpha range, you are lower bounding and upper bounding your alpha range based on the nearby opts that you know. Because your opt array is increasing on the row. And your opt array has a very good definition, which is that what's the best alpha for my DP calculation? And if I know that the best alpha for a DP calculation, which is ahead of me, has the alpha value as 6, then there is no point in me trying the alpha value of 7 or 8, which is like a larger value. Is this particular example clear? Like how we could reduce the search space for k comma 9. So now just like if you think about it algorithmically and not like a hard coded case, the general idea is that you first try to calculate k comma n by 2, which will take you some time. So in general, what you'll try to do is calculate k comma n by 2. It'll take you O n time. You'll get the opt value out. Then you'll try to calculate k comma n by 4 and k comma 3n by 4. One of them will take you time 1 to opt. Say this opt k n by 2 is actually the value is alpha n by 2. Let's call it that. So you'll go from 1 to alpha n by 2 in this one. And the next one, you'll go from alpha n by 2 to n. Total cost again is order n. And in this one, it's also order n. And if you keep on splitting, you'll see that each layer has at most order n cost. Because in the next layer, say the example, take the example k 3n by 8. In this case, you'll be looping over alpha n by 4 to alpha n by 2. And in the k n by 8, you'll be looping over 1 to alpha n by 4. And in the next guy, whatever that guy is, we'll be looping over alpha n by 2 to alpha 3n by 4, and so on. So total range will be again order n. And you'll have at most log n such layers. Do note that I'm not anywhere stating that this problem size, basically the 1 to alpha n by 2, this time that you're taking, is the same as this time, alpha n by 2 to n. I'm not saying that. I'm not saying that they're equally distributed problems, that they're same cost problems. What I'm trying to say is that the sum of the costs will be at most order n, because where the search function or the search range of one problem ends, that's where the search range of the other problem starts, and so on. So we are never trying to actually say that the opt function in itself, this alpha n by 2 value, will be balanced or will be like a middle value. We are not trying to exploit that fact. We are just saying that we'll calculate this value, and now we know whatever that value is, this alpha n by 2, it could be quite large, it could be quite small, that k n by 4 can be upper bounded. The search space of this thing can be upper bounded by alpha n by 2, and the search space of k 3n by 4 can be lower bounded by this thing. And you keep on doing it, like keep on dividing the tree. So implementation wise, it's recursive for this portion because it's a tree-like structure. It's kind of like segment tree-like structure, that you take a value n by 2, then you would say L is this, R is this, calculate the med, go recurse one level down. And you also keep on passing the lower bound and your upper bound. Originally, your lower and upper bound are 1 comma n. Later on, it changes to 1 comma alpha n by 2, and they keep on changing. For the implementation itself, I would recommend look at CP algorithms. I have it in my reference here. They have a very clean implementation for this. It's this link. So it's divide and conquer clear. Notice only thing we primarily exploited was the fact that you get this thing because of quadrangle. The monotonicity of the opt function. If you know your opt function is like a increasing array, you're done. You can apply divide and conquer. Any doubts on this? If not, I'll just move on to the next technique. So that's why if you have doubts, you can still go ahead. Cool. So now we'll go through 1D, 1D. Or before that, actually, let me just show you Knuth. I think Knuth is super similar to divide and conquer, but it's way less useful because like there are very few CP questions using Knuth. Knuth in general, like typically what it does is it helps you drop n cube time complexity to n square for TP questions. There is this blog post on CF, which is the main resource that people use to do all these GP optimizations. And you can look at that also for Knuth. I'll explain the high level idea. I'll skip this question in its entirety. But I've already defined the opt function, right? Okay, Saurabh actually asked a question. Why did you use n by 2? Did not understand that. That's a fair question. The reason we used n by 2 was it's a way to split the problem. I mean, going by the wording itself, we are trying to divide and conquer, right? In divide and conquer approaches, you typically split the problem at the midpoint. Say you did not start at n by 2. Say you took the entire array, for a given k equal capital K, and the previous array is already built, so you know that. Say you did the last value first. So you calculated small k comma capital N first. Now you've calculated small k comma capital N, so you know alpha n. That does not really help you in a very good way, because now what can you calculate? Maybe you can calculate this value and say that your alpha is upper bounded by alpha n, or you can calculate this value and say your alpha is upper bounded by alpha n. So you can reduce your search space, but the best way to reduce your search space is to pick the middle value, not because the alpha that it gives you is a very middle-ish value. Again, I argued just previously, like 2 minutes back, that the alpha it gives you, I'm not guaranteeing anything on that alpha. But what I am guaranteeing is that the depth of the tree will be at most log n, because if you start from n by 2 and you keep dividing on 2 sides each step, then you'll finish your recursion in log n steps. That's why, like, that's where you get the log. And on each layer, you also get order in computation. If you think of some other way of doing the computation, maybe not do it in this order, that don't calculate n by 2 first, but calculate some other value first, you'll end up with worse time complexities. You won't be able to exploit this bounded range thing as well. But like, it's a very good question. I mean, I see your point that it's not obvious on why we want to do it in this divide-ish way and not like some ternary approach, maybe like break it into 3 pieces. I think even that, like, those kind of solutions might also work. It's just that this one is quite good. I don't have a rigorous proof on like why this approach would be the best. I would assume it would have something to do with sorting, like why you can't sort faster than in log n in a comparison-based model. And like similar way, you could lower bound that why doing anything other than divide and conquer will not give you significant speed ups. That's my intuition. But yeah, but legitimate question. So for the Knuth optimization, generally it helps you to do n cube to n square. I'm skipping the question itself. You can look at it if you want. It's not that relevant, honestly. The important thing in Knuth is you want to prove quadrangle. You want to prove like one other inequality. Generally, that inequality states something like this: C a comma b. Again, C is the referent to that cost function. No, more like this: C b comma c is less than equal C a comma d, where a is less than equal b is less than equal c is less than equal d. That is the cost function from b to c is smaller than the cost from a to d, where a and d are a super segment of b to c. So if you have this inequality plus quadrangle, then generally you get this for free. And the main thing that you have to know for Knuth is that you want to get this somehow, this inequality, which, so notice the left-hand side part, this is basically just the divide and conquer inequality. That is opt ij is greater than opt ij minus 1, or you could have written it the other way, that is opt ij is less than equal opt ij plus 1, whatever. And that holds for all ij. I mean, that should be obvious. So the left-hand side of this inequality is just you get it for, like, if you can do divide and conquer, you get it in Knuth also. The other thing that you need in Knuth is the right-hand side of this inequality, which you don't get when you're doing divide and conquer. So you need a tighter inequality in some way. Like you need more constraints on the opt array. And the second constraint that you need is that even if you're incrementing the I to I plus 1, you'll still be moving your opt to the right. Right? Just assume for now that you get this for free somehow. You're able to, okay, and I mean, I'll share some ideas here on like how people go about these questions, right? A lot of times you can't prove quadrangle or you can't prove these kind of things easily. It's not straightforward to prove that this will hold or not, the IJ constraints. What sometimes people do, especially in the Olympiad setting, maybe it's relevant to ICPC also, you code up the question and you create this opt array in your implementation, the slow solution, and you do an assert. So you go over the entire grid and basically just assert for the statement over all IJs. And if this assert ever hits false, you just runtime error. All right. And then you submit this on the online judge. And if it runtime errors, you know that this constraint is failing for some test case. But if it does not fail on the runtime error and instead gives you TLE or something else, you're kind of confident that at least in the test cases that were small in size on which your slow solution was working, you did not encounter a assert. So that means this constraint was actually being satisfied. A lot of times proving this is a pain. So people go by hunch, that they manually work out a couple of examples and see that this condition holds, or they just random submit the Knuth optimized version and hope for AAC, or they do that assert trick if they are unable to prove formally that this condition holds. But you need this condition to hold for the Knuth to work. So let's assume for now that this condition holds for your DP. What this condition gives you is, for a given IJ, let's say this is your I, this is your J, this value, whatever this value is bounded by the J minus 1th value and the I plus 1th value. So maybe this is 3, this is 10. Then this value has to be between 3 and 10. Right? And the opt array. Yeah, so Shubham also shared a technique. He DM'd it. Maybe he can share it on the entire channel. I'm not sure if he's allowed to or not. But like what he said is he prints the opt array and looks for L-shaped increasing sequences of 3 elements for Knuth-related problems, which is a pretty smart way to do about it. Basically, notice that this is L-shaped, right? And he's like, I just print out the opt array and see that if I see a L-shaped thing, then Knuth works. Otherwise, Knuth doesn't work. Like L-shaped increasing thing. So the middle value has to be between 3 and 10. Not strictly between, but like in between. So it could be 3, it could be 5, it could be 10, it could be 7, whatever. And this L thing has to hold for every place. So even an L here, all these L's have to hold the increasing property. Right? That's also a pretty good way to go about this. And say you get this inequality for free in some particular question. Now what you can do is just your calculation, the way you calculate your DP, you have to be smart about it. You have to ensure that you'll calculate this value and this value before you try to calculate the I comma j value. And the way people do it, a common way is you go from I equal n to 1 in reverse order and j equal I plus 1 to n. Okay, notice also another thing. Yeah, maybe I skipped this portion, but like in Knuth optimization specifically, your I is less than equal j. Only then the DP actually holds some interpretable value. So the way you construct your DP, I'll just expand on this slide here. Like one way people do it is they start I from n and j from I plus 1 to n. So they first calculate. Okay, yeah. So I is less than equal j, and your eventual answer will be in dp1 comma n. That's the thing that you want to calculate. That's also another thing in Knuth. Generally, typically, I'm explaining the most typical use cases of Knuth. That this is where your final answer is. So in this case, you're trying to calculate this value, I think. No, my bad, this value. I is equal to 1, j equals n. I guess this value, I'm not entirely sure. But like, yeah, you go like this, basically. Your order of calculation goes like this. And in this way, you have calculated this 10 value already. And then you'll calculate this 3 value, and then you'll calculate all the following values. So when you're calculating this value, you already know the 3 and the 10. And that's why you'll only loop on this range from 3 to 10. You won't loop on any other thing. Similar to like what we were trying to do in divide and conquer, right? That we were trying to reduce our search space of alpha from 1 to n generically and wasting a lot of time there. You're only looping from opt I j minus 1 to opt I plus 1j. In this particular example, from 3 to 10. And that's your alpha ij is only possible to be in this range. And you'll keep on doing this. So for this guy, you'll be like, I'll loop from this guy wherever he ended and this guy wherever he is, and only try to calculate my DP for those values. And you'll keep on expanding this window and eventually you'll hit this guy. Yeah. And I think your answer will be somewhere in I1JN or something of that sort. Probably your answer will be here. That is INJ1. I maybe swapped something. So that's why the pictorial representation looks screwed up. But that is the idea, that you start from I equals n to 1 and your inner loop is j from I plus 1 to n. And that way you can calculate both things. So that's Knuth optimization. And the way, the reason why n cube drops to n square, this is pretty straightforward to see. Your total cost of doing all these things is, so you have n square states and each state used to take order and time. So that's why the original complexity was n cube, right? Your new complexity is for all I comma j pairs, your calculation takes time opt I j minus 1. Sorry, opt I, basically this much time, which is opt I plus 1 j minus opt I j minus 1 being double summed, right? This entire thing being double summed. Notice you have some terms being subtracted and some terms being added. If you sum up, open up this summation, you'll find out most of these terms will cancel out and only a linear number of terms will be preserved. Basically, terms of the form opt n plus 1 comma question mark will be remain, and on the right hand side opt question mark comma 0 will remain. Only these terms will be not cancelled out. And if you notice, the question mark can be from anything from 1 to n. And all these values individually will be upper bounded by n. So double sum, total complexity, whatever, like after the cancellations will be some number of terms, sum of some order n terms, where each term is at most n. So the total sum is at most n square, because you have around order n terms and each term is at most value n, because the opt value can never be more than n for anything, because your alpha can have, like whatever your alpha is, it's always from 1 to n. So your total thing is at most n square. So that's why the Knuth works fast. Basically, you get this double summation thing and you can argue that most of the things cancel out. Another way to look at why most of the things cancel out is think about the opt array, 2D array. Then you're basically adding a bunch, all these things, and you're subtracting kind of like this portion of this. So you're left with this portion, and each thing in this portion is at most n, and you have like n things here. So the total cost is n square. So that's Knuth optimization. I don't want to spend a lot of time here because honestly, I haven't seen Knuth optimization in practical use cases anytime. Like I've done some mock questions with Knuth, but I haven't seen it in contests a lot. So maybe it's just not that useful. Any questions for Knuth? Otherwise, we'll just move on to the last thing for the day, which is 1D 1D. Okay. If not, let's go to 1D 1D. 1D 1D is relatively unknown. I'd say the resources on 1D 1D, the good resources are these two, the blog post and this website. This website, like it's badly formatted website, but it's a good website. Also, you can look at Arjun Arul's video, which also explains 1D 1D very well. Lastly, in the further reading section, there is actually this other thing called Aliens Trick IOI, or like some other name also, Incredible Optimization, blah, blah, blah. You can read up the CF blog if interested. It's another fascinating DP optimization. There is this entire forum on CF, and you can see that like a lot of people have ideas on like why that particular trick works. It's not 1D 1D, it's something else. But nobody is able to prove why it works. So that's also interesting. It's also called as WQS binary search. And it was introduced in the Chinese Limited at some point. But like an interesting read if you guys are interested. Okay, so let's go over 1D 1D. So I would say, yeah, for 1D 1D, I'd recommend that just either go through this resource or the blog post or Arjun Arul's video. I mean, Arjun's video is pretty good for 1D 1D. So in 1D 1D, your general setting is that your DP is a one-dimensional DP, similar to say LIS, longest increasing subsequence, or something of that sort. And you are getting the quadrangle inequality. Therefore, you are getting the opt thing also. So you're getting monotonicity on opt. Do note that your opt in this case is just a one-dimensional thing. So you're arguing that your opt I is less than equal opt I plus 1 for all I. That is, when you're trying to calculate DPI, whatever alpha you pick to do the last split, that alpha always keeps on increasing as you move on your I. Something of that sort. Right? So that's 1D 1D. So the question that we'll be using is acquire from Spodge. And this question I also used for the CHT trick because coincidentally, this question you can apply CHT or 1D, 1D. And that happens a lot of times. Like same question, you can apply both the tricks and like both of them give you similar time complexities, or maybe you can apply divide and conquer or 1D, 1D, divide and conquer or Knuth. For example, in the Knuth question that I've shared with you guys, I know for this question you can apply divide and conquer also. That also works. You can later on see the question, but Knuth also works. So Knuth is better because it even drops the log factor. So what was acquire question? Acquire question is as follows. Maybe you guys were through the CHT blog, like video or not, I'm not sure, but like it's as follows. You have n pieces of land, pretty large, like 50,000, so you can't do n square. And each land has a width and a height, so it's a rectangle. And the cost is 1 square unit. So the cost of the entire land is like width times length, whatever. And you can do a large purchase in one go. You can buy a subset of plots, and the cost that you'll be paying for the subset of plots is the maximum width in that subset times the maximum length in that subset. And you cannot rotate pieces, like land pieces, you cannot rotate those rectangles. So if you buy a 3x5 and a 5x3 together, then you'll be paying, on the width side, you'll be paying the maximum width, which is 5. And on the length side, you'll be paying the maximum length, which is 5. So you'll be paying 5x5, which is $25. You want to make some purchases, no, ignore the word successive. The successive is actually different interpretation. It means one after the other in this example, but it does not mean sub-segments. The question is still subsets. So in this particular example, you can go about doing this, that one group has just 100 cross 1, the other group has 101 cross 100, and the third group has both these things combined. But if this example, and notice the first group costs you 100, the next group costs you 20 times 15, which is 300, and the next group costs you 100. So 100 plus 300 plus 100, total 500. That's the best way to do the subset thingy, like part. I'd use the word divide into subsets such that the union of all the subsets is the entire thing. If the input was 4, 100, 1, 15, 15, 1, 100, and 20, 5, the answer would still remain the same because you could still do 101 as one group, 15, 5, and 25 as one group, and 1, 100 as the third group. Notice the order of the lands do not matter. That's what I'm trying to bring home. The order does not matter. You don't have to pick contiguous subsegments or anything of that sort. You just have to pick like some subset such that all things are bought out eventually. And within that subset, the maximum width times the maximum length, that's the cost that you'll pay for that entire subset. And you want to minimize the entire thing. So that's the question. I hope the question is clear. So if you don't have any doubts on the question, I'll just quickly go over the 2 observations for this required for this question so that we can get to the final version of the DP and see what's happening, right? The 2 observations are, first, irrelevant rectangles. Some rectangles in this question are irrelevant. For example, if you have a rectangle of size 5 cross 5, or let's take some different example, like say 5 cross 10, and you have another rectangle of dimension, say 7 cross 12. That is, 7 is bigger than 5 and 12 is bigger than 10. In this case, this rectangle is redundant because in whichever subset you put 7 cross 12 rectangle, in that subset, just put the 5 cross 10 rectangle and you'll get it for free. That 5 cross 10 rectangle will neither contribute in the maximum width because 7 is larger than 5, nor in the maximum length because 12 is larger than 10. So all the rectangles whose width and length both are superseded by some other rectangle, all those rectangles are irrelevant. You can just throw them away. You can assume that whatever my optimal solution will be, I can just buy these out for free in my optimal solution, because wherever that superseded rectangle, like in whichever subset that superseded rectangle goes, I'll just clump this rectangle into that subset, right? So for all practical purposes, you can just stop thinking about these rectangles, which are like strictly smaller in both the width and the length from some other guy. So once you can throw away these rectangles, how do you find these rectangles? You sort all the rectangles by say width. So W1, H1, W2, H2, not H, I'll use the word length because that's what the question uses, and Wn, Ln, and you're getting that you're sorting by width, so you're getting sorted array in widths. Now, if you have some pair Li and Li plus 1, where even this is sorted, then you know that this thing is to throw because the width is also smaller and the length is also smaller, right? So just throw away all those things where the length is also smaller than the other guy, the next guy, meaning. And once you throw away all those things, what you'll end up with, the remaining array after throwing away those things, will be width 1, width 2, width n. All these are increasing. Length 1, length 2, length n. All these are decreasing. This is very interesting. Why? Because there will not be any consecutive pair of Li and Li plus 1 where this will hold. Because if this was holding, you would have thrown this out because this would have been completely redundant. So eventually you'll end up with an array where the lengths are decreasing and the widths are increasing. Right? So this is one land, this is one land, so on. And another thing you can note here is the second observation, which is contiguity. That is, once you have done this sorting, you can argue that your optimal subset cutting will always look contiguous. So you'll maybe put the first two guys in one chunk, the next two guys in one chunk, and the last few guys in one chunk. You'll never be like, I'll put W1 and W2, like the first and the second rectangle in one chunk, and I'll club them with the last rectangle, but not pick the things in between. Yes, Li and Wi are dimensions of one rectangle, of the same rectangle, more precisely. So you get contiguity also. I'll just give you the broad intuition of contiguity. Say your rectangles are R1, R2, Rn, right? Each one has a W1, L1, W1, whatever. And you pick a segment R2, R3, R5. Let's say you pick R2 and R4 in one chunk together. And you don't pick R3 in that chunk. Does it make sense? Let's think about it that way. R2 has W2, L2. R3 has W3, L3. R4 has W4, L4. We already know Ws are increasing, Ls are decreasing. So what will be the cost of clubbing R2 and R4 together? It will be the maximum width, which is W4, and the maximum length, which is L2, right? Out of W2 and W4, the larger width is W4. Out of L2 and L4, the larger length is L2. So it will be this much cost. Notice, if you had put in R3 inside, you would have got R3 for free. The cost for putting R3 inside was free because you would have still paid the same cost, because R3's width is also smaller than W4's width, and R3's length is also smaller than L2's length. So it never makes sense to create gaps when you're buying. If you're creating gaps, just put all the things in the gap in the same group and you'll still end up paying the same cost. So that's why you get contiguous property here. That if you're buying more than one piece of land in one go, they must be contiguous, because it doesn't make sense ever to skip a piece of land once you've done the sorting part and like thrown away the relevant rectangles. So you get these two observations quickly. I mean, part of the question is to get these two observations. So I'm not saying that it's easy to get these two observations. It's just that since we are discussing optimizations and not DP in itself, we'll skim over them. So once we get these two observations, our recurrence is as follows. DPI equals min of DPI, DPJ plus this much. Which is saying that for the first I plots, one way to cut them is that I do the cut at the jth position. That is, the first j plots go in one chunk or like whatever, some arbitrary number of chunks. And then from j plus 1th position onwards to the ith position, I take all those rectangles, sorted rectangles, and put them in one chunk. And the cost of that chunk will be the height of the ith chunk times the width of the j plus 1th chunk. Notice here, these are actually swapped. You can think of them. I'll just fix it the way I've defined it here. Since the widths are increasing, so I'll say r I dot w times r j plus 1 dot length, right? Since that's how we defined it. But the rest of the recurrence remains the same. And you'll try this for all j. So for all j less than equal I, you'll try to do this minimization part. And whichever one gives you the most, like the smallest value, you'll be like, that's my cutting point. So notice here, your K notation is something like that 1D people use. A lot of times Arjun used it, that blog post uses it. It's the same as the opt notation. So you can think of it like the opt notation also. So opt of I is basically the best J that helps cut for DPI. That's the definition of opt, right? And we'll show that quadrangle is satisfied in this particular question. And since quadrangle is satisfied, you get this. That is opt function is increasing in nature, or if you want to write it formally, opt I less than equal opt j for all I less than equal j, which is basically written here. And once we get this property, then we can show that we can actually do these kind of DPs faster than in square. Okay, so how do we argue about the quadrangle inequality? What is the cost function here? If you're going from A to B, your cost function is A rectangles length times B rectangles width, because your widths are increasing. So this is your Ath rectangle, this is your Bth rectangle. WA, WB, LA, LB. You know the length of this guy is bigger. You know the width of this guy is bigger. So that's why I did this, right? Or a better way to write this is maybe just simplify it to say WB times LA. Okay. Now, what's your quadrangle inequality? Quadrangle inequality says, say, just take these indices, A plus 1, B plus 1. Quadrangle says your CAB plus 1 minus CAB, that is the incremental difference when you expand AB to AB plus 1. This incremental difference has to be greater or equal the incremental difference had you started from A plus 1. We want to show this to be the case. We want to show that this is the case. How do we prove it? So what is this thing? This thing is WB plus 1 times LA minus WB times LA. And so this is the LHS. The RHS is WB plus 1 times LA plus 1 minus WB times LA plus 1. Notice on the LHS, you can take some stuff common, which is LA. And on the right hand side, you can take LA plus 1 common. So on the left hand side, you take LA common and you get WB plus 1 minus WB. On the right hand side, you take LA plus 1 common and you get WB plus 1 minus WB. Notice this portion is the same. You can just cancel it out. And it's also not, I mean, it might be 0. If it's 0, then both the things are just 0. So your inequality holds. If the thing is non-zero, then you could have canceled them out. If you could have canceled them out, you would have got LA versus LA plus 1. And we already know that LA is bigger than LA plus 1 because the lengths are decreasing. So that's why the inequality holds. I did it in reverse way. You could just go up and prove the quadrangle inequality. That's what I wanted to show you. that because LA is greater equal LA plus 1, you can multiply both the sides by WB plus 1 minus WB. And you can multiply by this because this is a strict is greater equal 0 value. Reason WB plus 1 has to be bigger than WB. So that's why you're not multiplying something negative. And you multiply both the sides, and then you expand them out and you get quadrangle. So you can see that quadrangle is satisfied. Is this part clear to everyone? That you can prove quadrangle to be true here? So now once you've proven quadrangle to be true, you're kind of done in the sense you get the fact that opt is increasing for free. The step, you get it for free. Otherwise, you could have thought about it intuitively also, that will my opt be increasing or not, whatever, as I increase my position. So this is the, like, this is one way to state your opt condition. The other way to state your opt condition is this, that opt I is less than equal opt I plus 1 for all I, right? Both the things are same. Okay, so now we've got the opt condition down. Yep, so let's work here. So now what do you want to show? Okay, now the main 1D part comes into play. Just getting this opt condition is actually not that, like, we are quite far from 1D actually being in place, because it's very magical of how it works. So you got this, and okay, I'll just replace opt with K because it's way less verbose and so easier to spell out or say. Think about how the K array will look like. K array will look like 1 1 1 1 2 2 4 4 5 7 8, something like that, right? Basically, K array will look monotonic. That is, it will be increasing as I keeps on increasing, right? Not strictly increasing. It can have the same value as the previous guy, but it will be increasing, right? So that's one thing. That's how your K array will look, and your DP array will also look some way. But notice you can only calculate your DP array from left to right. If you know the DPs of previous values, only then you can calculate the DP of this guy. Why? Because your DPI is dependent on DPJs or whatever DP alphas, whatever you want to call them, where on the previous DPs, these DPs. Each DP is dependent on the previous DPs. So you can't go divide and conquer approach or something. You can't say that I'll calculate some middle DP first, and then I'll calculate the left DP, right DP, something of that sort. Theoretically, if you could do that, you would have just gone and calculated DPN first and be done with the question, right? Because your final answer is in DPN. So why even bother calculating other DPs if you could just calculate DPN without knowing the previous DPs? So because DPI is dependent and it's only a one-dimensional DP, it's not a two-dimensional DP, you need to have all the previous DPs down before. This is pretty, I mean, it's a dumb thing to state, but it's necessary that I stated, because you can't, you can try to think of divide and conquer approaches, but they won't work here. And the reason is that. So you have the K array. Some people's original intuition of how they'll use the K array is, let's say I know K1, K2, K3. That is the opt value. And I also calculated DP1, DP2, DP3. Then maybe when I'm calculating DP4, at that point, instead of looping my alpha from 1 to 3, I loop it from K3 to 3. That is, I lower bound it by the previous value that I know, because I know my K4 has to be greater equal K3 because of the monotonicity. So I'll just, instead of starting from very first position, I'll just start from K3. And maybe that helps me out. It could help you out, but even in the extreme cases, it won't help you. Reason being, it could be the case that your K1 comes out to be 1, your K2 comes out to be 1, and so on, and your Kn minus 1 comes out to be 1, but your Kn is some big value, like say 12. In those cases, every time when you're calculating some ki, you'll be like, I'll loop my alpha from ki minus 1 to n or whatever, and your ki minus 1 will actually be 1, so it won't help you. I can intentionally make cases where your k value is very small originally and just jumps significantly towards the end. In those cases, you won't have any time savings because you'll still be looping over a very big search space each time. So you'll still run n square roughly, total complexity wise. So that's why this idea that I'll lower bound myself with the previous ki that I know doesn't really help you in those extreme cases. So this approach doesn't work. So typical ideas that divide and conquer and not use, you can't really use those ideas here. That's what I want to reason about. Is that clear? That like why you can't just do some basic manipulation over KIs. I hope that's clear. So what you can do is you can say, I'm just generically writing DPI, not for this particular acquire question, just generically writing DPI. Your recurrence looks something like this. Right? DPI is min over DPJs where J is less than I. Maybe you want to say strictly less than I because it doesn't make sense to go equal to I. And the cost is from J plus 1 to ith position. Right? And you're taking the min over them. Okay, fair. Let's say you calculate DP1 somehow magically. Right, I'll just add a page to this because we'll need a bunch of pages. Let's say I calculated DP1 somehow. Somehow meaning just I trivially calculated. It took me O1 time. Right? And I calculated DP2 also. Took me O1 time. Now I have my K array built up till this position, which is 1, 1. And I just hypothetically think that my remaining K array will also look like 1s. Right, in the future, hypothetically. Now, when I'm trying to calculate DP3 or something, so my idea is basically that I'll keep on gradually fixing my K array. Originally, I just get the worst representation of K array, which is just a bunch of 1s. And then I'll gradually fix my K array each time and keep on calculating one more value of DPI. So originally I have DP1 sort like set up correctly. Then I have DP2 set up correctly. And I have some incorrect K array, slightly incorrect K array. Then I'll calculate DP3, then DP4 and so on, and keep on gradually fixing the K array as well. That's the high level idea of 1D 1D approach. So when you're calculating DP3, notice when you're calculating DP3, if you can ensure that your K3 is calculated correctly, you're done. If you can ensure that your K3 value has been calculated correctly, you are done at that very point. If your K3 is 1 and you know for a fact that K3 is 1, then when you're calculating DP3, you can just calculate it in O1. You'll be like DP3 equals DP1 because K3 is 1 plus cost of 2 to 3. I don't even have to try other candidates because I already know what my K3 is. Right? But you could argue, okay, maybe you can know K3's value. And so you calculated K3 and you got the DP value, say the DP value comes out to be something. Ignore that value. Now, when you're calculating DP4, you can't be like that. I already know K4 also, right? You can't be knowing the entire K array already. So you have to update the K array to ensure that it's correct for a given prefix. Ensure that it's correct up till the 4th position and so on. So originally your K array looks like 1, 1, 1, 1, 1. Right? Now, when you're calculating DP2, say you have DP1 calculated, which is basically a no-op, it's some base case. When you're calculating DP2, your high-level idea is that in the second position, my K can either be 1. Okay, no, I'll explain it the other way. Say this is your array, 1, 1, 1, 1, 1, right? Maybe this, now when you're trying to put the value 2 and think about all those places where 2 could come in this K array, that is, all those DPs where cutting at 2 would have been a useful decision. You could binary search for that. What I mean is, you could think of this value, say this is index 1, index 2, index 3, index 4, index 5, index 6. You could be like, for index 4, whatever DP that is going to hold, basically DP4, would cutting at 2 make more sense, or would cutting at 1 make more sense? That is, for DP4, would alpha be 2 at better, or would alpha at 1 be better? You could compare those. So you could be like, I'll compare DP2 plus cost of 3, 4 with DP1 plus cost of 1, 4. And maybe one of them wins. Maybe alpha equal 1 wins. So I'll let it remain like this, the array. And then I could binary search to the right. Maybe try it for 6. So for 6, if I'm trying alpha equal 2 versus alpha equal 1, what I'm basically trying is DP2 plus cost 3, 6 versus DP1 plus cost 1, 6. Which one is better? Maybe this guy is better in this case. Then you would update your K array to look like 1, 1, 1, 1 followed by 2s. All 2s. Reason being, if 6 is your cutoff point, that is at 5, 1 is better, but at 6, 2 became better. Because of the monotonicity of K array, you know that at 7 also, 2 will be better than 1. Cutting at 2 will be better than cutting at 1, even for the 7th position, even for the 8th position, and so on. I'm still not saying that I have the entirely correct K array. I'm just saying that this array looks better than the previous array. And now, when you say I'll start introducing value 3 also in my K array, you'll be like, I'll again binary search for 3 in this entire array and see where it starts beating the previous guy. What's the first position, the leftmost position, where alpha equal 3 starts beating alpha equal something less than 3. It could be some 1 position, it could be some 2 position. So take an example. Originally the array is 1, 1, 1. Maybe after your first binary search, you find that this array is better. Maybe after your second binary search, you find this array is better. Maybe after the next one, you find this array is better. It could be possible that 4s when came up, they just beat this one only. And maybe at the 5th position, you find something else, and so on. So you'll keep on updating your K array each time with a new element and try to find binary search where does it start beating the previous thing. And the nice property that you get with this iterative logic is your K array prefix starts getting accurate as you move on. So originally, your first position is correct for K, then your next 2 positions are correct for K, then your next 3 positions are correct for K, and so on. And the benefit of this is that you can keep on calculating new DP values because you are keep on finding the correct Ks for those DP values. So let me just run a simulation here. I mean, it's not that easy to explain this optimization, honestly. So let's say your K array is just 1, 1, 1, 1, 1 originally, right? You calculate your DP1 base case. Now you come for K equals, you try to introduce value 2 in your case. So you come up with say 1, 1, 2, 2, 2. In your binary search, you figured out that your K array improves only at this point. What I mean to say is that DP4 got improved, but DP3, DP2, DP1 did not get improved, right? The binary search just showed you this. Now, when you try to calculate DP2, you'll be like, what's my second element in the K array? It's 1. since my K2 is 1, I have the correct value of K2 up till the second position. Reason being, how do I intuitively say this? Why is K2 of 1 the correct thing? Because your K array, which is the optimization array, has already taken all the candidates from 1 and 2. So your K2 is 1. Since your K2 is 1, you can just calculate DP2 in a go in O1. Now you'll fix this array again, your K array, and introduce 3. Maybe after introducing 3, your array becomes like this. My bad. Actually, let me just make this example like this so that it's better crafted. Yep, maybe your array becomes like this. In this case, you look at the third position, which is K3, which is 2. So you'll be like, I can calculate my DP3 in O1. Reason being, I'll just pick 2 as my optimal cutting point, and I won't put any more brains to it. And I conjecture here that your K array is accurate up till this point. And your K array was accurate up till this point at this stage, and your K array was accurate up till this point at the stage. And in each iteration, your K array will become accurate up to a one more element position in the next iteration, and so on. That's what my conjecture is. I mean, yeah, and it's pretty much done if you can get this conjecture out. The reason how you prove that this conjecture holds, like why is your K array accurate up till a certain position is, I mean, in the base case, it's obvious that K equal 1 for DP1 is obvious because you can't be cutting before DP1 and for the first example. Once you have DP1 calculated and you binary search for 2 in a specific position, you'll find 2 to have the cutoff at some position, maybe here, maybe somewhere to the right, whatever, right? Notice that wherever you find that cutoff of 2, your first 2 positions will now be fixed. Reason being, your second position will either get the value 2. In this case, it got the value 1. It could have gotten value 2. It could have never gotten the value 3 or 4 or something. If you're trying to calculate DP2, your K2 will always be less than 2, strictly less than 2. And similarly, whenever you're trying to calculate DPI, your Ki will be strictly less than I. Because of that, because your Ki will be strictly less than I, you can be ensured that once you've introduced value 1, value 2, up till value I minus 1, all of these values in your K array, after that point, you can be ensured that your Ki value, wherever it is in the array, this is your ith position, your Ki value, since this has to be less than I by definition of the K array or the optimization array, whatever you want to call it, by definition, this value has to be less than I, and you've already introduced all of these, like using that binary search idea. So your ith value has to be correct. It can never have a value larger than I or like greater equal I. So whatever value it has at this point is the correct value, because in the future, when you introduce I plus 1, whatever, those values can never impact the K of ith position, because K of ith position has to hold a value less than I. It can never hold a value greater equal I. So all these values are redundant for K of I. Is this part clear? I can explain like how the exact, like, I mean, just the DP calculation part is O1, which is easy to see in this case because your K value, when it gets fixed, you can just quickly look at it and be done. But like, how are you updating this K array smartly so that you can like keep on referring it and like do the binary search thing? That part is still like not obvious, and like, but it can be done in like total complexity and login that I can show. Smart thing again, please. Smart thing again. I'm not sure what you're referring to, Saurabh. Allocation of K. So, okay. So the high level idea of 1D was that you'll create the K array originally with just ones. And at each step, you'll fix the K array slightly. Originally, the K array only has ones. You'll be like, I'll introduce value 2 to the K array. So at some point in my K array, my monotonicity will be like that at some point, twos will become better than ones. And the cutoff point where twos become better than one, I'll find that using binary search, right? I'll try for each index, whether say this index is the fifth index. So I'll try whether DP5 is better for K equals 1 or K equals 2. Someone unmuted themselves. Was someone trying to ask questions? How to smartly assign the repeating values? Did not understand that. Okay, fair. So this is question. Yeah, this is a slide. So let's say your K array is originally just ones, right? Now you come in and say, I'll introduce the value 2 to this array. You'll just binary search for the first place where 2 is actually better than 1. When I say this, what I mean is, say for the fifth position, you say total number of elements are 10. So your cutoff, like your midpoint is fifth position. You're trying to binary search and you say you find this position. What you'll question is DP5 better off if it uses the cutoff point as 1 or cutoff point as 2? Meaning, so since this is a minimizing DP, you'll compare DP1 plus cost of 1 to 5. What is this LHS? It's basically what the value of DP5 would have been had you used J equal 1 as your cutting point. Or your RHS, which is DP2 plus cost of 2 to 5, or whatever you want to call it. Like, and you'll be like, I'll compare both these values. If say this value is smaller, that is J equal 2 is better. I know for a fact that in the K array at the fifth position onwards, twos are better. And not just on the fifth position, but even on the sixth position and so on. The reason I'm saying that you can assume that it will be better even on the following position is because of the monotonicity. If K increases even at one place, it increases at all the places on the right hand side. It can't be the case that the array looks like 1, 1, 1, 2, and then another one. This is not allowed because the K array is monotonic, right? So, but okay, but my binary search has still not finished. Maybe 2 is also better somewhere here. So I won't stop doing my binary search at this point. So say for K equal 5, I find this to be the case that 2 is better. So I'll try for this point, K equal 3. So I'll compare DP3 for J equal 1 or J equal 2. Maybe J equal 2 actually becomes larger. That is DP1 plus cost of 1, 3 is actually larger. So J equal 1 is actually better. In that case, I know my cutoff point is either the fifth position or the fourth position. So I'll try the fourth position also. So DP4, both with J equal 1 or J equal 2. Maybe in this case, J equal 2 actually turns out to be better. And I'll actually do those computations. I'll calculate this value, I'll calculate this value and do the comparison. But it's O1 in each case. And my binary search in total will take just log n time to figure out the cutoff point. So once I figure out the cutoff point, say 4 is the cutoff point, I know that my array from 1, 1, 1 now gets converted to 1, 1, 2, 2, 2, 2, 2, 2, 2. Is this part clear? How we've binary searched for the value where 2 becomes the better choice the first time. And now we'll say again, introduce threes in this same problem. So maybe threes start from here. I mean, it can never start from the third position. That's just dumb because third position's K3 has to be less than 3. That's what I was saying earlier, that Ki has to be less than I by definition of K. But 3 could have started from somewhere here maybe. That is possible. Or it could have just overwritten the entire 2 chunk. That's also possible. And so on. So the way people implement this is generally using a stack. Notice this entire thing of ones, you can write this as 1, 10. That is, you have ones, you have 10 ones. So originally your K array could look like this, a pair of 1, 10. It's a, you could think of it like a stack or a queue, whatever. A stack is probably the natural representation. And then your stack becomes K equals 1, 3, which means you have 3 ones followed by 7 twos. So your next element in the array will be 2, 7. And next your array will look like, let's just take this example to be like this, 2 twos followed by 3s. So your array will look like 1, 3 followed by 2 twos followed by, I don't know, 5 threes, something of that sort, right? That's how your stack will look. And the way you'll manipulate the stack, so when you're after this stage, when you're inserting K equal 4, like the 4th position in this, what you'll do is you'll look at the top of the stack, see if you're beating this starting point, that is this point or not, using K equal 4. If you're beating it, you just pop out the entire thing. Now you look at this chunk. Are you beating the starting point of this chunk? Maybe you're not beating it. Then you'll binary search in this chunk and override the first point where you are beating this chunk. So either you're beating the entire chunk because you're beating this value. In this case, you just pop out the entire thing, or you're not beating that chunk's starting value. In that case, you know that within this chunk, there will be some position where I'll start beating it. And then you binary search within that chunk. And insert that thing in. And now that's how your stack will look. You'll update this thing because maybe I'm assuming here your thing looks like 1, 1, 1, 2, and then 4s. So that's how the update will look like on the stack. So that's how the stack implementation works. You push for a given value once, you pop for a given value once, and you do some binary searches. So amortized complexity of the number of insertions and number of pops on the stack is O(n). And whenever you're doing an insertion on the stack, you're potentially doing a binary search. So that's where the log n comes from. And you're doing like n pushes on the stack. So that's why the n log n. And the DP calculations themselves are just O(1) because you already know the correct K whenever you're calculating a DP. Maybe you guys are still slightly confused about 1D, 1D. If that is the case, I would recommend to go through Arjun's blog or like Arjun's video, basically. I think he explains it better than I do. So maybe that's another resource you guys can look at. Any other questions? Cool. Then yeah, I'll stop the recording and thanks a lot for joining the session.